Is it safe to live next to a power line? High voltage can kill a person in a split second. Can you touch a bare wire and stay alive? And is it possible to put a hand into an aquarium with a bare wire? And are there any wires that don't burn? Let's start looking for answers to these questions right now. Electricity from power plants comes to cities over high voltage lines. And here comes a problem. Near power lines, the electric field is great. Great enough for this fluorescent bulb to light up in my hands. But there are children playing nearby. How dangerous can it be? Now let's deal with it with the help of an expert. Alexander, why does the lamp glow under the power line?
Well, if we put it simply, it's due to the difference in potentials. The further the lamp's ends are, the brighter it will glow, provided one end has a maximum value and the other end minimum. But this doesn't mean at all that when the lamp is lit, this is guaranteed to be in excess. And vice versa. If it doesn't glow, there is no electromagnetic radiation.
Now we'll measure the intensity of the electric field at the level of the human head.
Under the power line, not more than 5,000 volts per meter is allowed. Well, here it is now 761 volts per meter. It even corresponds to the maximum permissible level simply in the local area, without a power line.
But can you live here, right under the tower?
You can't live right here, because if we, well, design an apartment, then in the apartment not more than 50 volts per meter is allowed. In other words, there is almost a 1.5 volt excess.
Okay, well, the houses that stand straight along this line.
As you move away from the power line, the values fall gradually. With the values that are now under the wires, you can be sure that there won't be an excess in these buildings.
Residents of houses beyond the sanitary protection zone of the power line, which is 20 meters, have nothing to be afraid of. But specialists who serve these lines cannot neglect personal protective equipment.
This is basically a very serious blow to the immune and cardiovascular systems of the body. In other words, it affects blood cell formation.
How to protect the body from the impact of a powerful electric field. To find out, we went to the Research Institute of Occupational Medicine. Here, tests of protective suits for power engineers who have to work with high voltage are carried out. Nina Borisovna, what conditions can be recreated on this testing stand?
Well, it's a specially designed test stand that allows you to create high levels of the electric field of the industrial frequency.
From an ordinary person's point of view, this air condenser is more like a grill.
It's not a grill. Why?
Yes, well, that is, there are no discharges between these plates.
No. Just to the top plate of this capacitor from a high voltage transformer, which is behind your back. High voltage is applied.
The sensor is placed in the dummy. It will show the strength of the electric field. First, we will test it without a protective suit. It's forbidden to stay near the stand during the test, so we will observe it from a screened room through the window. We start with 5 kilovolts and gradually raise the level to 60. This is the electric field that appears near power lines. The sensor inside the dummy records values fatal for the body. And now let's repeat the experiment. But first we'll dress the dummy in a protective suit. Let's see how well the suit protects, relatively speaking, when an installer rises to the connected power line support in real life.
Raise up to 60. (150 millivolts per meter).
But under the suit, the value is safe for life. And now we have 136 millivolts.
This is actually the background level.
So that's 100,000 times smaller.
Yep.
It's amazing. Why is there such a reduction in voltage?
Such a decrease is due to a very good design of the kit, which provides full electrical contact of all its parts. The man is placed in a Faraday's cage.
The installer is protected from the electric field, but on high voltage lines there might also be unexpected situations. You can see in the laboratory how an overhead power line works under high voltage. Alexander Vasilievich, this crack, what we hear right now, is the same. It has the same origin as that sound on a power line, right? This characteristic sound.
Yes, that's right, Alexander. This is a corona discharge. In the electrode system, coaxial cylinders, high voltage is applied to a thin electrode, and the electric field that arises in this case allows the creation of the corona discharge.
The potential difference is so high that even air, a dielectric, begins to conduct electricity. For power engineering, this phenomenon is very unfavorable. The corona discharge is a loss, and in addition, all elements of the power line suffer from high voltage. Now, at this training stand, we are modeling a situation that could even lead to the destruction of the insulator. Do I understand it correctly?
Yes, with prolonged exposure of this situation to the insulator.
And why does the insulator suffer?
It is because of high temperatures of about 10,000 degrees and powerful ultraviolet radiation. And insulators, which are made of a fickle dielectric, a short-lived dielectric, they quickly break down. But even a durable dielectric with long-term action can fail.
If you just stand under the line, the arc discharge is not dangerous. But when working at height, breakdown is possible even on the switched-off line due to induced electricity. So a person working at height needs reliable protection. A multi-purpose suit should protect a person from an electric field, electric shock, and the risk of being burned by an electric arc. And how real is this protection? We will try it on a dummy that imitates a human body. Even its resistance is equal to the resistance of the body, -1 kiloohm. The suit is not an insulator. A different principle works here. It's just a very good conductor, and the entire charge, like in a Faraday cage, goes over its surface without getting inside. And can we now test this suit here in a mode beyond the limits of man?
Yes, we can. We can now pass through the suit a current of about 30 amperes.
But for a human, what current is fatal?
At a current of about 30 milliamperes, cardiac fibrillation occurs.
And we are now supplying the current of 30 amperes, that is 1,000 times more than
That's right.
the current that can kill.
Yes.
And we are now in the danger zone. So we leave and start the experiment.
Let's start.
So, let's sum up. On the body of the dummy, the current was 3.3 microamperes.
That's right.
And on the outer 100, on the outer surface of the suit,
Through the test suit, we passed a current of 36 amperes,
so
1,000,000 times more powerful.
1,000,000 times powerful. And while the current, which was directly on the dummy, is almost 1,000 times smaller than a life-threatening threshold.
Yes, that's right.
Then I have a question. There was smoke. We saw it. And even this area has some, well, not charring, but smoldering of the fabric. What is it? Why did this happen?
The fact is that we tested a sample of the suit at such current values which are off the scale. And even with such values that practically, in practice, they can occur. Yes, a suit, as you can see, it has not lost its protective properties.
The costume is woven with metallized fibers a few microns thick. They are conductors for electricity, and the fabric itself consists of aramid fiber that can withstand not only high temperatures, but also combustion. Well, Andre, then there is an unusual question. Can this suit protect from An electroshock weapon.
Yes, it can.
Let's try. At least the glove.
Tell me how I should hit you.
Gently. So here we remove the fuse. That's it. Then you press the button.
Well, how does it feel?
I just closed my eyes. Can you do this again? I don't understand.
Ah, it struck me. And you?
You were struck a little. No, amazing. Yeah, looking at these miracles, I regret about only one thing. I didn't have a suit like that when I was doing electrical wiring at home. People on power lines, of course, need protection, but the power lines need it too. And the main danger for power lines is thunderstorms. Supports are always the highest objects on the ground, and they become an excellent target for discharges from the sky. To find out how power lines are protected, we went to the laboratory of the Moscow Power Engineering Institute. In this laboratory, scientists create artificial lightning to learn how to defend themselves against the forces of nature. This is a villa community model. It's impossible to guess where the lightning will strike. Lightning conductors on houses are approximately on the same level. And can we now hold a small test? First, without this mast, which will play the role of lightning protection, just to see where discharges will strike. And then, putting it approximately in the center to compare the results.
Of course it can be done.
To tell the truth, I cannot wait for the lightning to feel like Zeus, the thunderer. You just tell me what to press.
Well, with respect to Zeus, the thunderer, it is a very great responsibility, and you need to click here.
Well, let me now install a lightning rod on the model and repeat the experiment. Now the lightning strikes exactly in the metal mast. Such masts connected with a ground loop also protect transformer substations. But when it comes to high voltage power lines, this solution isn't suitable.
For a power transmission line with a voltage class of 110 kilovolts and above, cable lightning receivers are used, which are installed above the phase wires connecting each support. And these lightning protection cables are connected to the supports. And each support is, as a rule, a reliably grounded metal structure.
These constructions are tested on the same laboratory models, and the cable lightning receivers regularly take on new and new lightning. This system works practically without failures, and yet there are rare hits in the phase wires. If the lightning bursts through the lightning protection, the surge discharge immediately diverges in both directions from the place where it struck. But further on, the switchgear automatic shutdown is activated, and this reliably protects the equipment. Automatic shutdown in general. This is the main way to protect against emergency situations with electricity. This also works in our houses and entrances. How to make and test the right wires. This factory produces cables and wires for a variety of tasks. There are shops where wires for household extension cords are assembled, and there are also shops where complex shielded cables for active zones of nuclear reactors are manufactured. But it all starts with raw materials, huge copper wire bundles with a diameter of 8 millimeters. One of such wire bundles can be turned into 42 kilometers of 3-conductor cables, which are usually used for heating electrical appliances and household extension cords. Then the copper wire is set into the drawing machine, where it is stretched to the required thickness up to 1/10 of a millimeter. In the next shop, the conductors are twisted and insulated. Ready-made wires and cables must be tested, and there is a laboratory on its own which periodically carries out tests. All cables manufactured at the factory are tested in this laboratory. Well, here they are cooled to minus 60 degrees. And here, heated to plus 350. In this cell, their resistance to excess humidity is checked. At this stand, the cables are checked for breakdown at high voltage. But at this stand, for example, you can check the resistance to multiple winding. Well, it's important, for example, vacuum cleaner cords. There are specialized wires and cables. They are produced entirely with other machines and undergo even more stringent checks. On this machine, fire-resistant cables are braided. The metal is covered with this ribbon. This is fiberglass, which is covered with mica. And its most important task is not to burn in the open flame. We can do this for a very long time with a lighter, maybe even a soldering lamp, but this insulation won't lose its properties. Even our simple test shows that nothing has happened at all, although they are much harder tests than such cables undergo in certification centers. Central Research Institute of Building Structures, named after V.A. Kucharenko. Here, fire-resistant cables are tested with an open fire. Let's check how conventional and fire-resistant cables differ from each other in all characteristics.
Let's do it.
Why do you connect the cable to electricity?
To check if the cable will work under voltage and fire.
Well, you are testing it under real-life conditions. For each cable, specific parameters are set. How long it should be in an open flame and keep working. That fire-resistant cable, which we will test right now, must withstand at least 2 hours. So, time determines whether the cable passed the test or not.
Yes, in other words, the time just shows how long the cable can withstand the fire resistance.
Yeah, well, let's light it up.
Okay.
It's been almost 2 hours. It retains the most important thing, its work capacity, despite the long-lasting effect of direct flame. The modern industrial electric power industry is a search for trade-offs between costs for transmission of electricity and transmitted capacity. The classical approach puts engineers in very rigid borders. And while all the acute problems are solved at the moment, nevertheless, there are scientists who offer a radically different approach to solving old problems. It is based on the discovery of the physicist Nikola Tesla, made by him more than 100 years ago. This is a high-frequency electricity laboratory of the Research Institute of the Electrification of Agriculture. This is an aquarium with usual tap water. The voltage decoder is connected to a standard current of 220 volts at 50 hertz. But the frequency at its output is 500 times bigger, 25 kilohertz. Thin wires are connected to the decoder and to a 1,000-watt halogen lamp at the other end.
This unit transmits 1 kilowatt and 1 kilowatt.
1 kilowatt.
1 kilowatt of power.
By such thin wires.
By such thin wires.
And what would happen if we set the standard 50 hertz and 220 volts?
They would overheat. They would be overheating of insulation. They'd get out of order and melt some part of the insulation and ignite the surface on which they lay.
Sergey says that you can put your hand in water with wires since high-frequency energy is safe for people. Ah! I'm joking. Listen, well, if I hadn't seen it with my own eyes and hadn't put my hand in it, I wouldn't have believed it. I'll tell you honestly, we have already conducted such an experiment, only there we lowered the lamp to a gas of fluorine ketone. Well, it is also called dry water. It's an absolute dielectric. That is, when I put my hand into that aquarium, nothing threatened me because this liquid doesn't conduct electricity. It's just usual tap water. And I guess that if this light bulb was now powered by a regular power supply, I'd be killed.
Yes.
This is possible because the currents of high frequency go over the surface of the body, over the skin, and the worst they can do is burn it. The current doesn't pass through the human body as through a conductor, and therefore doesn't affect the vital organs. In addition, according to scientists, you can use very thin wires for high frequency and even create single-wire power lines, which can save a huge amount of metal. The idea is good, but for the industrial scale, this principle isn't suitable. Experts of the Moscow Power Engineering Institute are sure of this.
The idea of single-wire transmission lines and wireless transmission lines appeared a very long time ago. I would like to point out their peculiarity. The authors of this idea always suggest using it at high frequencies. But at high frequencies, any transmission line turns into an antenna, and as its size grows, it increasingly emits electricity into space in directions perpendicular to the direction of energy transfer. That is, energy doesn't reach the load, so the efficiency is sharply reduced.
In turn, environmentalists fear that when transmitting high-frequency electricity on an industrial scale, the air will be contaminated with electromagnetic radiation, and this, as we already know, can harm living beings. Perhaps that is why so far no high-frequency lines are used anywhere in the world for electricity supply to industry. But high-frequency electrical engineering can be successfully applied in other areas.
It has its own specific, successfully developed goals, and it's implemented in a useful application for both civil and special purposes. Microwave ovens are also a high-frequency power. Microwave technological systems are like drying, heating, induction heating. There are many applications of high-frequency electrical engineering. But I must say that today, it's universally agreed that using high-frequency techniques for transmitting energy is unpromising on an industrial scale.
What will scientists offer us in the field of electricity transmission? What will the power lines be like in the future? Time will tell. In the meantime, one thing is obvious. To transfer electricity from the source to the consumer is a task which isn't less difficult than to generate electricity.